I'm Michael Bowling. I've been a prof here for 21 years. I work on reinforcement learning. I've been thinking a lot about continual reinforcement learning. That's what we're going to talk about today. If you're just walking in, you might not realize there's still seats up front. There's at least 4 seats in the very front row, even some seats elsewhere. You don't have to stand at the back. Okay, so I want to talk about continual reinforcement learning. I should first recognize that I've been talking about these ideas with a number of people, even more people than I put on this slide, but Ezra in particular, who I saw somewhere, we put together a paper for RLDM on this topic, and there's a group of us that are trying to work to extend it further. Martha and David Sikrovsky, who's actually not here, he's at the Charles University in Prague, and David Shabashvari. But I also want to give a shout out to Dustin, whose work in strategic games has actually carried back over. It's very weird to think that we went from, we learned something in multi-agent and we're going to come back and apply it in the single agent setting. Usually it goes the other way, but maybe this is an example of something going that way. So thanks, Dustin. Okay, we all sort of, many of us, I don't know, I actually don't know if all of us understand the reinforcement learning loop. I'm going to make some assumptions to get to the continual learning part, but we have some agent. It's operating in the world by taking actions on the world, getting some observations back, some rewards. The goal is for it to take actions to accumulate more rewards in the world and to maximize the amount of rewards it accumulates in the world. We're interested in continual reinforcement learning where that agent has to keep learning, has to keep discovering new things about the world. And one of the reasons why we think that's important is something that really developed here at U of A called the big world hypothesis, that says, well, the real world we care about, the complexity of deploying an agent in our world, the one that we think about operating in, that world's enormous. It doesn't fit on our screen. That's how big it is. It's actually bigger than that. But when we take actions in the world and get observations, we're not going to really be able to understand that world in its entire complexity. It's too big for us to model it entirely. We're always going to struggle to understand. It's always going to appear, maybe even non-stationary, as if it's changing on us because it's too big for us to discover all of its intricacies. And that's why we need to continually learn about our world. Now, if you're sort of wondering, haven't heard this idea before, there's a couple of arguments for why the big world hypothesis might be true. One is, well, there are other agents in this world that we're imagining. They too are trying to think about the world, and we're thinking about them in it, trying to figure out how this world works. So we'd have to build a model of them, building a model of us, of building a model of them. Like this recursion sort of has some problem. There's even yet a different reason, which is we're in that world. Like we don't normally think about it like we have some RL agent operating in Atari. That's the agent's not really in Atari, but we are. We're made up of the matter and atoms of the universe. Alan Watts said, through our eyes, the universe is perceiving itself. Like it's really deep. We are part of the exact world that we're trying to operate in. You are part of that world. So that means that we have to understand ourselves, understanding the world, understanding ourselves. Like that's the complicated problem we live in. And that's why we have to continually learn about our world. Okay. Let me shift gears a little bit. You have probably, if you read papers on reinforcement learning, you have come across something that says decision read over that. The I think this might be a problem. That's going to be the premise of this talk, is I think that might in fact be a problem. Well, I think we are making very good progress on algorithms and coming up with new algorithms for reinforcement learning, for continual reinforcement learning. I think we might be limiting ourselves in our ability to advance as far as we need to. I do want to give a shout out to Amir Masood, is giving an online talk later today that's going to be on rethinking reinforcement learning, a very similar title to mine. We did not coordinate. He's going to talk more, as I understand it from the abstract, on the algorithm side. And what I want to do is think not actually about the algorithms. Okay, so we could talk about the algorithms for continual reinforcement learning, and I think that's going to be a place that this research is leading towards. But I actually want to think about the box that the algorithms inside of reinforcement learning live inside of. Because there is a box, there's a set of things that we expect our algorithms to do or adhere to, or the kinds of problems that they are expected to solve, that is a box that we put our algorithms in. And once we settle on that box, we are going to devise a certain set of algorithms, certain kind of algorithms. If we choose a different box, we might get different algorithms. And so what I want to do is spend time thinking about that box and then questioning that box. Yeah, so let me say, what are the things I'm going to question? There are going to be four sides. There's a box here. There are four sides of the box. Let me talk about the four sides of the box. I already gave a hint of one of them. We generally think that we expect our algorithms to live in the world of Markov decision processes. I'm going to come back and talk more about these in a minute, but let me walk through the four things. One, we have a set of evaluation metrics that we expect to evaluate our algorithms with, and that we're going to try to see certain lines go up when we evaluate our algorithms. We have a certain set of environments, a certain set of benchmark environments or standard ways that we run and test our algorithms in, and we would expect our algorithms to do well on those environments. That's what it means to get our paper so that we can submit it to NeurIPS or RLC. But lastly, I think, and maybe the most important one, the one we don't think about even nearly as much, is that in reinforcement learning, there is a deep, deep focus on what I'm going to call artifacts. And I think that's a big problem. Okay, so that's going to be the overview of the four things that I want to try to deconstruct today. And then the second thing I'm going to do is I'm going to build for you a different box. I'm going to put four new things down for those sides that are going to replace these four things with some alternatives that might present a different perspective on where we go from here. Yeah, so there was a question right at the end there that was asking what do we do inside of continual reinforcement learning? I don't know. There's going to be a myriad of problems. This feels to me like we, especially if we're about to replace almost all of the foundations, which I think we need to do, then we're going to have a lot of work in front of us. All of it is good stuff to do, and I think we need more people doing it. It's kind of one of my goals is to help you start deconstructing the box too, and maybe have more people advancing what I think is needed to get us closer to actual continual reinforcement. Okay, let me tell you about this box that we've stuck ourselves in and see if we can't push down some of the sides of this box. Okay, the first one, I said maybe the most important one, is we have a focus on artifacts often in reinforcement learning. It is common that we'll think about our agent interacting with the world, and we'll even talk about as our agent as if it is training, that is, if it is sitting there interacting with the world, and its job at the end of that training is to produce something like pi star, or maybe a particular value function, the optimal value function. That's what I mean by artifact. I mean by a thing that you can point to that's outside of time, that just is. And so we think we interact with our world through what we call training, and then maybe out will come pi star, and then we'll test that thing. We'll go and see how well does it do in the world. Very, very common. Like how common, oh, maybe I should point out one, that's what I mean by artifact. How common is it? Well, like kind of every celebrated result in reinforcement learning, like DQN, yep, did training and then tested it in Atari environments. AlphaGo did self-play training, came up with a policy, and it landed and was tested against Lee Sedol. Work that I've done in DeepStack, flying balloons in the stratosphere, driving race cars, all of this are examples of did training, came out with some policy or some value function, some artifact that was then used and evaluated. I think this is where the problem is. Continual reinforcement learning can't be about that. It can't be about the artifact because we're constantly learning. It has to be about something else. Okay, second one, Markov decision processes. So what do I mean by that? Well, I never finished the tuple. I said it's defined by a tuple. It's defined by a tuple with states and actions, transitions, and rewards. Here, I should put that up there. Yeah, and then what do we get from this? And then we often later in the background section, we might then define Q star is the solution to the Bellman equation. It says that if you recursively apply it so that it satisfies this recursive equation with rewards plus the next transitions plus the maximum of the Q values at that next state, that gets you an optimal Q function. And from that, we can get an optimal policy. We're doing that, remember, because we cared about artifacts. The Bellman equation allows us to now point to artifacts as being our answer. But now to get there, there's a little bit more going on that sometimes you don't put in papers. Yeah, Barbara. Thank you. Randy,
So about buy-in, an old guy spoke about the Turing Gödel Hawking challenges 2 weeks ago, and Michael noted the recursive nature of the RL continual learning sketch at a high level. Is any redrawing of the box motivator respectful of those challenges? Ooh, that feels like a super deep question. I don't think it was. I don't think I've given this much thought, Randy, and maybe it needs more thought. I think that's probably the shortest answer I can, the best answer I can give. Okay, so we have these states, actions, transition, reward. Sometimes we don't say this, but we often mean, oh, by the way, the number of states is finite. The number of actions is finite. The transitions are Markov. I mean, that's pretty much in there in the Markov decision process definition. So are the rewards. But there's also other things we're talking about, like the transition function, the whole world is ergodic or communicating or unichain, or pick whatever word you want for the idea that you can actually get from one state to another state reliably, that you can actually see the whole world repeatedly over and over and over again. That's not true of real worlds. That isn't, the ergodic property is probably the least thing true of real worlds. Let me just give a little simple example of something that's not ergodic. We could have some agent operating in the world, and maybe at time step one, that agent, having never seen anything about how the world works, has to choose to go whether to go left or right. And if they go left, for the rest of their life, they're going to play rock, paper, scissors against Bart Simpson, who always plays rock, good old rock. Or if they go right, they will, for the rest of their lives, have to play AlphaGo against, or have to play against AlphaGo in a game of Go. AlphaGo is presumably beatable. It's probably not perfect. You keep learning. Maybe you actually figure that out. But that decision for which the agent couldn't possibly have known whether to go left or right will entirely control what rewards it actually gets from that environment forevermore. Can't go back. That makes it hard. Like, do we really expect that this agent then should learn that it should get a reward of, say, 1 on every time step, and it should find that optimal policy where it ends up going left and then play against Bart Simpson? Is that a reasonable expectation that our learning algorithm should just do that when it has no basis for knowing how that decision should be made and it can't go back and make it again? Another example is, like, not all of you decided to come to this talk, and you can't go back to that moment before you decided to come to this talk and say, what if I didn't come to this talk? Right? Everything in our life is not ergodic. We never get to go back and see states again. We, in fact, just continually experience the world constantly changing in front. Okay, so I think that's a problem, and I think the continual learning agents, that's what they need to deal with, but our Markov decision processes don't let us deal with that. They make us deal with the fact that everything is reliably repeated. Okay, what about these evaluation metrics? Well, I can put up a plot. If you're a reinforcement learning researcher, I can put up a plot, and I can label no axes on this plot, and you already know what's going on, right? You know that this is probably some notion of time or amount of training data or something, some amount of learning is going on. This is performance, probably like expected accumulated reward. And we can look at this and we can be like, you know, hey, that blue algorithm is doing pretty well. It's like, it's probably optimal. Like, I don't even have to tell you that the top bar up there is probably like, that's probably reaches the optimal policy. Like, it's found the artifact. And we can look at that orange line and say, that's kind of disappointing. It's not really learning very well. Now, if we go back to that previous example, what if this blue line is the thing that went left and just played Bart Simpson the whole time? This orange line went right, and it's actually learning to beat AlphaGo in a short period of time. Like, which one's the better learning algorithm again? We really think that blue is the better one because it shot up really fast? That doesn't feel at all right to me. That's not how we compare algorithms. But that's what we do. We do expected return as the comparison, and that's how we run our algorithms. Okay, environments. You know, I said we care about the big world of my hypothesis. We imagine we're this agent operating this super complex world that we can't deal with. Like, what's one of these big worlds that we tend to run our algorithms in? We run it in things like Atari. Atari is, let me tell you about the Atari. Atari 2600 came out in 1977. That was a really long time ago. I was just born. Most of you probably were not. You know, the Atari 2600 had 128 bytes of RAM. And I didn't misstate that. It had 128 bytes of RAM. It had 1,024 bits. That's the entirety of its working memory. The cartridge itself, of course, had code on it and other things. The ROMs could range between 4 and 16 kilobytes. Let's take a look at DQN, beats Atari. Its replay buffer is 6 to 8 gigabytes big, has 1.7 million parameters. You know, it would not run on an Atari 2600. It would not run on a machine 10 years after the Atari 2600. It would not run on a machine 20 years after the Atari 2600. It runs on our machines now. This is not the case of, you know, a little agent dealing with a super complex world. I mean, what we actually tend to run on is we tend to run on big agents running on little tiny worlds. And that's the default that we're used to. It makes sense that we could probably find the optimal policy in this little tiny world because we have the capacity to represent it all. Okay, so here, I want to say one more thing before I jump on, and I was hoping there'd be a slide for this. Those four sides of that box, maybe I'll go back and show. One of the things that's really difficult about it is some of these are cherished things that we've all been taught in reinforcement learning. They're at the beginning of textbooks. They're at the beginning of every paper. It's hard to throw away cherished things. But there's another problem. Every one of these is self-reinforcing. If you were to decide, maybe I don't care about MVPs, but I'm still going to evaluate with expected return as my basis, and I'm going to look at the environments we typically look at, and I'm going to focus on artifacts, the only option you have is to go back and use MVPs because that's what gives you pi star and Q star. And if you were to say, well, let me try to come up with new environments, but I'm going to expect that I find optimal policies in them and I'm going to test things on expected reward, you will just bring back the same kind of environments we're used to using, episodic, fairly small testable. So the difficult part is that you can't really question one of these. You just end up putting it back again. That's the nature of boxes. The other side is predetermined by the other three. So what I want to do is I'm going to question all of it. We're going to throw this all out. We're going to try to rebuild it all from scratch. Okay. Back to, if I can get back to there. Back to this. Comments, objections, questions, where are we at? Yeah.
But then isn't like everything an artifact? You mentioned pi star, but even if we're like continual learning, we start caring about pi and we can stop it halfway. Okay, how's pi doing now? And so it still feels like it's an artifact, but it's not 5-star yet. So I guess like, what are your thoughts on that?
In the paper, we gave a little bit more, an extra word. Forget what word we used. It basically meant it was the word we used is atemporal. So a pi star is an atemporal artifact. It doesn't matter where you are in time, what's happening, like what you've experienced. This is the right answer to the MD, right? I'm going to give a solution where what we're going to care about is, you know, maybe pi over time. I'm going to care about behavior, and that is not atemporal. I can't talk about behavior without thinking about its sequence and adaptation over time. And I think this is what we ultimately should be caring about is behavior. How does it respond to how does an agent respond to the experience it has? And that, I think, is more temporal. It's rooted in time, whereas pi star is not. We don't put a little t on. Yeah, Sheila. Yes, I will attempt to remember. The question was, isn't everything an artifact? How can you reject artifacts? And I think what I'm rejecting is atemporal artifacts, things that are things that you can imagine converging to, for example, because convergence is a property that is now atemporal because it's about what the limit of time. Yeah.
Michael.
What the question is, then for the experience, what then is now communicating in the next times I haven't so the last time I think I think so I think life is just learn from the past.
Yeah. This is the challenge. So the question, I totally understand the question. The question is, I sort of set it up that you never get to repeat anything again. But of course, the basis for learning is that there's something about that past data that tells you something about the future data. Like obviously, if that doesn't happen, what does learning even mean? I said you couldn't change whether you can't go back and say I'm not going to come to Michael Bowling's talk, but you could also not come to my next talk. Of course, you don't know exactly what's going to happen at my next talk, so you're not really certain about what that choice is going to be. But yes, we need to have a basis for learning. If the answer is I throw everything away such that there's like nothing possible to be learned, then we do have problems. Hopefully I will address that as we go on, but I think that's an important consideration. Yeah.
So when you were just talking about like the big agent having a small world, it sort of evoked the idea of agency in me, meaning that the agent has like has a much higher level of control over its environment than in a big world. And I was going to ask, are we considering that also in this discussion? Thinking about the level of control or influence the agent has on its environment and the amount of expectations we would have of it. Since all the benchmark environments, we sort of expect it to do the thing that it could do, but
right.
How would you know that?
I think a principle that I particularly embrace is that I think we should make as little assumptions about the environment as possible. But of course, if I have very little controllability on the environment, then I should have very little expectation that I can control the environment, right? But the agent shouldn't need to know that in advance, or should not only work on environments where it has a high degree of controllability. I think we want to have agents that are very, very general, but naturally, if the best you can do is this amount of ability to accumulate reward, then that's the best you could like that. That's going to be what we expect from it.
Just to continue on that, for example, as humans, we have some level of control in our environment, but we don't know if that's the best level of control we could ever have. So is our expectation, okay, our agents should just become as good as humans, or because we don't know really the real world, the big world we live in, and how much control we could possibly have over it.
All I can say maybe is I'm going to give a mathematical proposal of maybe what answers this question, okay. but I'll get there shortly. There's a question online from Rich. Is an artifact the same as a model? Wow, the word model is really overloaded. And so I don't know how to, like, in the sense that like every neural network is a model, then maybe. I think I care, Rich, about the changing of things. How does an agent is defined by it's a change in its behavior as it gains experience, and less about the moment to moment, like maybe it constructs a model of the world, but that model of the world is likely going to be changing because, again, big world hypothesis, I can't find a single model. If we expect the agent to converge on the optimal model of the world or a particular model of the world, that's probably a mistake. That's an artifact where we're trying to reach some temporal conclusion, atemporal conclusion. Yeah.
I don't know, maybe this is like a guess to see how we can remove some parts of that spur. But if we want to, for example, set our goal to very abstract, we just want to know the environment without any reward or any kind of, I don't know, some reward that we're going to gather. Then we can say, okay, we want to, maybe in this sense, for example, we can remove the pilot star as the artifact, maybe the evaluation, and maybe, for example, only the MVP and the environment is the thing that we want to learn. And then as soon as we put some rewards as the goal, then the optimal policy, Q star or whatever, and the evaluation comes to be, right? So I think it kind of depends on how you formalize your goal, or is there any reward or something?
The question asked is, if we're going to think about removing parts of this box, then doesn't that depend on like how do you formulate your goal? In particular, if maybe we could just say remove rewards as being the focus of the goal. I mean, the way you pose it, I sort of felt like your goal is saying, well, then my goal is to sort of learn the MVP, like learn a model of how the world works. That still sounds like an artifact again to me, because that's atemporal. It doesn't depend on, where I am in time. Like it would just be a static thing that I would eventually converge to. And then when it's needed, like by definition, I would just stop learning because I've learned it. And that doesn't feel like continual learning to me. And I think I'm not rejecting the goal. The goal remains accumulate reward. That is the agent's goal. Nothing has changed there. Yeah. So I'm not feel like maybe you're tearing down even more of the box. Maybe that's worthy to tear down. We should reject is reward the notion of driving our goals and behaviors that we want our agents to do. And I guess I'm not. And that way I'm still doing reinforcement learning. Our goal is to accumulate reward. Yeah, Karan, one more question, and then I'm going to jump.
In motivating example was, assuming time step 1, you pick your rest of the world. Is it going to be hard or easy?
Yeah.
While that is true, and that could be happening in some world, is that a world where it's interesting for us to be in?
it might be the world we're in. And then do we want to judge our algorithms on their ability to do that when they have no basis for being able to do it?
So is the proposal to have something that's
Okay, I'll come to the proposal. It's also possible that maybe you get to repeatedly do that decision. Maybe that wasn't the only time. Someone came back and said, well, do you want to go left or right? I'm going to offer you that decision again. Do you want to go left or right? And we might then start to judge our agents differently. Then if the agent continues to go in, getting defeated over and over again by some impossible to beat Go playing program when it could have ended up playing rock, paper, scissors against something it's easy to beat and get lots of reward, I think then it's fair to judge that, right? But is it fair to judge it if it's a one-off decision? And I think there is a lot of one-off decisions for which there is not a background of data that could actually influence that decision. Okay, let's try to rebuild this box differently. Okay, so I'm not going to focus on artifacts. I've already sort of alluded to this. I want to break this down. I don't think that we have separate training phases where we then output some artifact that we might test that. My answer is there's just experience. And all it is, one long chain of experience. Training is testing in the sense that every time you experience a new thing, that's a new test example. And then after you've experienced it, it is now part of your training to experience the next testing, right? All your data was at one point your test data, and now it becomes your training data. Your new test data is what's about to come in front. The future is test, the past is train. Everything just moves in that direction. It's all just one long stream of experience. So there's no special notions of where we stop and then we have to output some answer. And that's why we have to continually learn, because the future might be different than the past. So what matters is behavior, not artifacts. Okay, so that's the first point. Second one, let's talk about what we can replace MDPs with. My goal is to make as little assumptions now about the environment as possible. So I want to replace it with the least assumption place I can, which is just say that what there is histories. There is just a history of experience. And so we can think about histories as being just tuples of agent got to take an action, then got an observation, and a history is just some finite length sequence of actions and observations. And then an environment consists of something that takes a history, agent's next action, gives you a distribution over observation. That could be utterly arbitrary. I'm going to make no more assumptions about this at all. An agent, we can think about an agent as being just the other side of this. It takes a history and it outputs an action, some distribution over action. So I'm going to start as generically as I possibly can, and I'll do my best to make no more assumptions. Maybe we'll say that A and O is finite. We could probably also do countable, but let's not worry about it. We'll assume that it's finite. We might do a little bit more. Maybe we want to decompose our agent. This is a common thing that people have talked about is what if the agent has some ability to construct something that it thinks of as state? Now, this is not actually state. This is not like state in an environment. This is just something the agent believes that I could build up a notion of what similarity does this have to pieces in the past. So it might have a state update function that says, well, if I think I was in a state and I took this action and got this observation, it gives me some next state that I think I might. And then maybe the agent reasons by trying to figure out, okay, if I had that, how should I map states to actions? And that's how it's going to think about its policy selection. But notice this is just a decomposition of the agent. Nothing is happening on the environment side. I'm just thinking about the agent might think of itself this way. A solution might be to first figure out how do I construct state and then figure out how do I act given that state representation. Okay. All right. So the bulk of this is then going to be on these evaluation metrics. What are we going to do to evaluate these things? Before I get there, let me just point out that, okay, our agent living in some long lifetime of experience, that's what's meant to be drawn here, going from left to right. The agent is moving through time in some long continual stream of a history that it observed. We can think about the environment it is in as being, it defines what are the probabilities of these observations over all kinds of trajectories, right? All of them, all of these trajectories that didn't happen, it could have gone down here, and it has some probability of what would happen in all these spaces. So we can think about this triangle of the environment as all possible histories that could occur. There's a moment in time in the future where when the agent gets here, right, gets to that point, there's a new environment. There's a new world. The agent is at this point, and now there's a probability for various outcomes given all the histories that it could place. This world is not the same as the world it was in before. This would not be true of MDPs, right? If you were an MDP and you acted for a little bit, you're still in that MDP. But we are not in the world that we started. This world has, it looks just like every other world. It has a distribution over the next observation, given the history of actions and observations that have occurred, but they will be different now. And if I keep acting, I'm in a new world. Every step I take, I generate a new world. This is true of you, by the way. All of us in the room, we are creators of worlds. We make worlds as we act in the world. This moment in time is the beginning of a new world that I'm operating. I contend that a good learning agent is one that is well adapted for the worlds that it finds itself in. We had an agent that is a good continual learning agent. It would be well adapted to each of these worlds it finds itself in. Yeah.
Sounds like the worlds is not the same as environment.
I'm going to use world felt fancier to me, and creator of environments doesn't sound as
But then
cool as
the
creator of world. But sure, let's say there's a
Well, sure. But the point is that the way you defined environments like previously,
yeah,
so you're saying at every step that changes too?
yeah, because the environment is a function. It says, given this history in the next action, what's the distribution over observations? And that changes if we were to start history here, and if we were to start history there. You are in a new world, you're in a new environment by the mathematical definition of these history process environments. And then a bazillion hands went up. Yeah.
But you have a new same app that's just taking like input, or do you mean like that app is a change in function that is not switching?
I mean, it is like we can go back to the mathematical definition here. This function E now is a mapping from history to action. It is a new function E. Like the way you could derive it from the other function E, but it is now a new one. You are in a new world. You know, what might be possible in one world is no longer possible in this world. So I think in every way to say, I think it's fair to say the world has, the environment, the world has changed. Yeah.
It's not a stupid question, but how is history different from experience?
One is an object that the agent builds for it to do its whatever computation it wants to do. Here, I'm just referring to history being like, it just exists. This is the history of actions and observations that you have seen, whether you wrote them down or not. You might have written them down, and you could have stuck them in a replay buffer, but you also might never have written them down and put them in a replay buffer. Okay, bazillion questions. Yes.
So you say the states here is not the states we were mentioning before in the older definition. So what could be the definition of these as?
It's not going to be. It is just something the agent builds. The agent could just say, "I'll take the last few observations and call that state." Is that state like so? In Atari, for example, common Atari agents, we stack the last 4 screens on top of each other and say that's state. But is it state? I mean, no. Like, there's no reason why that is in fact the state of the Atari emulator. The agent just declared that as state, and there's an update function that says when you get a new observation, kick out the older one, stick this one in, and it just takes the last 4. That's what I mean, it's just an arbitrary choice the agent made to try to make sense of it. Yeah.
Same question. If the environment is changing at every time step, wouldn't you want to subscript it with things?
I mean, you can. I can now talk about E of like H of T. For a particular history, there's a new environment that starts at that history. And in fact, mathematically, we might actually do that in the paper. But yes, every history starts as a beginning of a new environment. Question online. Yes, the function E is the same, but I think he means that the outputs given the action are changed. Maybe Dustin is answering. I think Dustin might be answering someone else's question. That sounds like an answer to me, not a question. Oh, maybe, okay. I think, okay, so Vlad asked, does the history just change, but the environment function E is still the same? I think there's just two ways to look at this, and I'm not saying one is better than the other. I just want to point out the other way. That you could say, I'm in environment E and I have changed my history. And all I'm saying is that I could also say that at this moment, replace the environment you're in with this history with the new environment that just starts from that moment where that is the beginning of time. That is a completely also valid way to talk about it. And I think because of that, it gets me this notion that we are in fact creating worlds. And then I think it also gets me this notion that I want to think about agents that are well adapted to that sequence of worlds that it finds itself. Yeah.
Just wanted to clarify that if the agent takes an action, so the world will be different because it considers the it's an action or it isn't.
Yeah, so here, let me go back. Actually, this is the one I want to go back to. Because I'm saying, well, once you define a particular history, that changes what your environment is going to be doing going forward. Then, action is right here. Like I'm having control over those, like I do take action, then that controls the environments that I see. Yeah, Mark.
If the environment is changing at every step, if there's a new world, how can we measure performance in a world that we only seen one step?
Okay, I'm going to move on and say, here's how I think we should think about measuring the performance of our algorithms. And now this looks really complicated all of a sudden. So let me try to break it down for you. The first part over here just looks like an agent return. It is absolutely just an agent return. I'm going to sum up some rewards, given that I'm following a policy at time t. I'm going to take my actions according to those policies, and I'm at history HS. So I'm going to, this is now my return if I started at the world that starts at time step S. Okay, so this term is the agent's return. This term is some other alternative return. It's something else I could have done. It's going to start at the exact same history, HS, and it's going to accumulate sequence rewards, but it's going to presume I acted in a different way there. And it's going to apply some deviation to the agent's policy, some change that I could have done instead of the thing I've been doing. We can think about this deviation as it really does take the policy in. It can just change some small aspect of the agent's policy, or it could replace it entirely. It might say something like, every time in the morning that you took your raincoat, what if instead you took an umbrella? That could be the change to your policy. Otherwise, you're going to do everything normally that you would otherwise do that day. It's going to change this one aspect to your policy. So I want to ask, I'm going to compare how well you did to what if you applied this deviation to that policy. Now, there's a bit more going on, so that together is a deviation regret. It's saying, how much regret do I have for not having made that change to my policy? I'm going to, in fact, apply that uniformly over time. Like the next few things I'm about to say is all now making it possible that you could actually control this deviation regret. So what we're going to do is imagine, I'm going to ask myself, what if the whole time I look back over all of time and I say every single time I want to imagine, what if I would have taken an umbrella instead of a raincoat, rather than just on February 7th. I'm going to say every single time I'll make that change to my policy, and I'm going to sum up in total, take the average of how much I would have regret for not making that policy change. Yeah.
I was struck by this formulation being a comparison between what we did and one thing we could have done, where there are potentially many other.
Yeah, so I'm going to define this for a single deviation, and then what we're going to imagine is that there's a big class of deviations, and I want to make sure with none of those do I wish I would have done. Yeah. Okay. Yeah. Okay. Yeah.
So for the agent to take, I understand that you've experienced the rewards, so now you have a memory of all the rewards that you experienced. But then if you're trying to see the deviations, where are those rewards coming from?
This feels it feels impossible, right? Yeah. There's a counterfactual on the left, and I never get to revisit anything twice. How could I know what would have happened if I would have taken an umbrella? That seems like a big problem, and I'm going to not answer that problem. Maybe at all, because I have 8 minutes left. Let me point out a couple of things, or maybe one more thing. Because of this averaging, notice that one moment at the beginning of time, we talked about this illustrative environment where I could go left or I could go right. I might have some regret, like maybe I can't figure out how to compute it yet, or maybe it's incomputable entirely because of counterfactuals, But if I could compute this, it would say I have some regret if I went right for not having gone left and just being in an easier environment. But over time, if I never get to revisit that decision, that regret on average will just vanish. Like a single moment in time is not enough for me to persist at regretting something. I have to repeatedly see it for me to regret it. Like I have to repeatedly make that same mistake. And if you only have to make it once, then that 1/t will wash that out. So this is addressing this problem. We're not going to be mad at agents for making decisions that they couldn't possibly get right because they had no way of knowing. Yeah.
Good question. One, this is a random point, right?
Oh, these are random variables, yeah.
So I'm trying to minimize the random variable. Like how?
The goal here would be to try to make deviation or regret go to 0 or to not grow quickly.
Or variance, some sort of utility over this random variable.
I'm not sure which random variable you're pointing.
The
whole thing.
Yeah. That's random, right?
The expectations, I think, probably kill all the randomness. Maybe there's some sort of outer expectation that says, I don't even know what history you're going to actually take.
Yeah.
So maybe there's still one more random variable involved. But if I actually just talk about this quantity on the history I actually took, then there's no more random variables. And that's the one I actually care most about. Not sort of what happens on average, but what happened on your experience.
How is this different from you talk about swap regret in online?
It is there. I am going to steal liberally from the online learning community and without hesitation or pause or any shame. So if you see connections, then yes. I am literally not inventing anything new yet, except for I think everybody thinks that this is crazy to begin with, but I'm not inventing anything new. Another point to just make is that regret has now become very local. Like I'm not going to think about what would happen if like I only applied the deviations to the policies I followed, not to other policies. I only care about the histories that I actually saw while I was learning. I don't have to think about some other possibilities that are further global afield. I'm going to skip over that to try to actually finish on time. How do I do that? Let me come back to return to this in a minute. But let me really quickly say the fourth wall was environments. Right? So we've covered 3 of the walls. The last of the wall of the box was environments. We normally are running environments where we're really big and agents are really small. I'm not going to propose to you an environment that we should run in continual learning, but I do think that we need to, an answer that sometimes people give is, well, let's just run it on bigger environments. We'll keep making our agents really big and just run it on even bigger environments. And that will get us closer to the big world hypothesis. And I think that's foolish. I think that all we're going to do is make it really hard to do science if this is what we do. I think the way forward is that we have to get used to not running our agents on big environments, but in fact, thinking about really small agents running on even kind of small environments. Like if we're going to run on small environments, let's just run with really small agents. That will help us understand what happens in the big world picture better than dealing with big agents do. And maybe one way we can do that is throw other agents in those little environments, and that might get us a continual learning problem. But I think that is an open question. Like we're going to have to try to figure out how we come up with environments. And I just want to point out that if we keep running our continual RL algorithms on environments that don't need continual learning, we're unlikely to see that they're doing something interesting, right? So I think there is as we make progress, we're going to need to do something on environments to actually find some that illustrate what it means for algorithms to continually learn. Okay, I'm really out of time. Maybe what I'm going to do is say there are many objections that one could have to this. Number one, the deviation return seems like it's an unknowable counterfactual. How could you possibly cover that? Super quickly, the agent's return is actually I can get an estimate of that expectation. In fact, my history gives me an estimate of that expectation. This one, I can actually get with importance sampling. And the requirement I need on that importance sampling is just that the agent's behavior is closed, that the support of the agent's behavior, it makes choices that have enough randomness in it that it covers the deviations as well too. And I can actually estimate an unbiased estimator of that expectation on every time step. There's a little bit of extra work needed to actually show that that means that you can create a consistent estimator of this, but we can create a consistent estimator of this with one trajectory through, and we don't have a problem with the counterfactual. Another objection, deviations give an alternative and unknowable sequence of worlds. Like, if I did follow the deviation, then I wouldn't be at the same place I'm at right now. So you saw a sequence of worlds, but if I actually applied the deviation, I'd see a different sequence of worlds. Yep, totally true. And that's just not what we're going to do. The objective says, like, so this is a notion of policy regret. If you looked at RL terms, sometimes they'll talk about policy regret as being, I have some regret for doing something different. And I'm going to care about how it would have led to a different distribution of environment histories. And we're just going to not. Partially because you can't, like, unless you can do the ergodicity assumption and repeat things, you can't answer the question of what would have. That is an unknowable counterfactual. But I think this is still a reasonable thing to ask, which is, do I wish I would have done something different in the worlds I found myself in, and the environmental situations that occurred to me? Do I wish I would have done something different? And I think that's still a reasonable objective, and it's something we can compute and optimize for. Another issue is that deviation regret, turns out it does not order agents, and this is an actual problem. So normally when our go-to evaluation metric is we're going to measure expected return. And then, whatever agent has better expected return, we say that did a better job. Here, if I have a different agent that is a different algorithm, it's going to see an entirely different set of worlds. And so how it did in its set of worlds and how you did in your set of worlds are just kind of not comparable. I think this problem is something that we should learn to wrestle with, because it's just true, right? Like, what I managed to accomplish in the worlds that I found myself in, and what you managed to accomplish in the worlds you found yourself in, how could we possibly compare our learning apparatus and algorithms from what the outcomes that happened there? Like, I think that's just a reality of something that's unknowable, and I think we should start getting used to thinking about that and not worrying too much. That means we don't get to totally order our outcomes. Another point is deviation regret could encourage agents to reach a place where no learning is possible. Like if you can just get to a place where you can't learn anymore, then hey, you have no more regret and life is great, right? So instead of that left and right, what if left was, I just go to a place where I get zero reward, doesn't matter what you do? That means I have no deviation regret, because it doesn't matter what I did, I'm doing the best I can. And that's kind of true. And if it really was a time step one, if some agent went there and had no deviation regret, well, I mean, it did the best it could. I don't know that I can fault it. Now, if it has an option of getting out of there, then that's a different story, right? And so maybe it's hard to get out of there, and it's a long horizon problem to get out of there. And I think we can handle that. I think we can talk about horizons in this deviation regret growing over time, so that you considerably think about larger spaces. You have a larger horizon that you're going to check your consequences of your actions on, and the consequences of these deviations. And if there is a way out of there to get back to that decision and go here, then I can start blaming an agent for not doing it. Okay, that is all. I'm over time. I apologize. Some of that was technical difficulties, but anyway, thank you so much for your attention.